Now we are moving toward the lecture 3, that is on digital codes. In this lecture, we will be discussing digital codes. The topic that is to be covered in this lectures are Introduction to Digital Codes, Binary Coded Decimal (BCD), BCD addition, BCD subtraction, access-3 code, access-3 addition, access-3 subtraction, ASCII code, gray code, binary to gray code conversion, gray to binary code conversion, and some examples. Okay, digital codes. In practice, the digital electronic required to handle data which may be numeric, alphabets, and special characters. This requires the conversion of the incoming data into binary format before it can be processed. This is various possible ways of doing this, and this process is called encoding. To achieve the reverse of it, we use decoders. So, as a statement, we see that for all this data, we require some digital codes. This digital code can further classify as weighted and non-weighted codes. Okay, in weighted codes, for each position or bit, there is a specific weight attached to it. For example, in a binary code, each bit is assigned a particular weight to n, where n is a bit number and n is equal to 0, 1, 2, 3, 4, for which the weight are 1, 2, 4, 8, 16 respectively. The example of this type of code is BCD code. Non-weighted codes are those codes which are not assigned with any weight to each digit position. Okay, and that is each digit position within the number is not assigned any fixed value. So, example of such codes are access-3 code and gray codes. Now let us see these codes separately. In this series, first most fundamental code that we normally use is binary coded decimal, that is known as BCD. BCD is a weighted code. In weighted code, each successive digit from right to left represent a weight equal to the sub-specified value, and to get the equivalent decimal number, add the product of the weight by the corresponding binary digit. For uh, for the BCD part, 8421 is the most common uh, technique that we use. Let us understand with an example. For example, if we have a number 567 uh, decimal, now if I have to code it for BCD, or especially for 8421, so 5 can be written as for a group of 4 bits. It can be written as 1010. 6 can be written as 0110, and 7 can be written as 110. This is 8421 format. That means for each digit and for each decimal digit, I am defining an 8421 code. 8421 stands for the weighted positions. Third position is having weight 8, and third position is having weight 4. Second position is having weight 2, and the last zero position is having weight 1. In such a way, so for 5, that is 1010. Similarly, for rest of the numbers. Other than 8421, there are several other codes. 6311 code, which we can define this number. 45421, we can define this way. But the most popular is 8421. We normally do the BCD code in 8421. Now, let us see how the arithmetic has been operated in the BCD code. In this series, let us first of all see the BCD addition. The addition of a BCD is performed by adding 2 digits of binary starting from LSB, okay, LSD or LSB. In case if the result is an illegal code means if it is greater than 9, okay, or if there is a carry out, or if there is a carry out of 1, then add 0110 Okay, if there is any carry out, then also you add 0110, or if it is an illegal code, then also we add 0110 to each and every group, each and every digit which is converted to binary code, and add the resulting carry to the next most significant digit. Okay, now let us understand it with an example. For example, this is 679.6, which is to be added with 536.8. I have written a BCD of this. 6 is can be written as 0110, 7 can be written as 0111, 9 can be written as 1001, point 6 can be written as 0110. Similarly, 5, 3, 6, 8. Now adding these numbers. Adding these bits 000, 101, 101, 01, 10 again 1, 011, 011, 101, 110, 1 carry, 1 plus 1 is 10, plus 1 it is 11, 1 again carry, you are getting 1 plus 1 equals to 0, 1 carry, and so on, and similarly the last one. Now we find that each and every code, PCD code, are illegal because they are more than 9. 9 is nothing but 1001, that is represented as 9, and each and every code is more than 1001. Now, as per the definition, if there is an illegal code, so in that case, you simply add 6 equivalent of 6 is 0110, each and every code. Now, after adding 00 is equal to 0, 1 plus 1 is equal to 0, 1, 1 plus 1 is equal to 1, 2 plus 1, 1 plus 1 is 0, 1, and so on. So we are taking the consecutive carry to the next code. As the carry is generated, you will be taking the carry to the next code. Similarly, here also the carry is generated, it is taken to the next code, and so on. So we finally get this code. Now, to get the resultant in the decimal form, convert each and every code to the decimal part. 001 is this one, this is 2, this is 1, this is 6, this is 4. So the answer is 1216.4. Or if you can check it directly, it is the same as in the case of decimal. So this is how the PCD addition is done. PCD subtraction. The BCD subtraction is performed by subtracting the digit of each 4-bit group of the subtrahend from the corresponding 4-bit group of the binary in the binary starting from the LSD. If there is no borrow from the next higher group, then no correction is required. If there is a borrow from the next group, then 6 is subtracted from the difference term of this group. Let us understand this statement by an example. Now, in this example, we have to subtract 147.8 from 206.7 using 8421 BCD code. Now, as I am doing, I'm subtracting. This is 1 minus 0 is 1, 1 minus 0 is 1, 1 minus 0 is 1. Now, for this subtraction, for you have to carry borrow 1 from here. So 10 minus 1 will be 1. So the borrow is present in this group. Similarly, we find that again there is a borrow in this case. For example, if this 1 has been borrowed from here, so here it is left with 1. 1 minus 1 is equal to 0. Here it is left with 0, so 1 is borrowed from here. So 1 0 is minus 1 is 1. And then again 0 is left over here. So again I required a borrow from here, which is borrowed from here. So a respective borrow has been taken from the MSB group. So again there is a borrow in this group also. As it is already our 0, so one borrow has been taken here. That means it is also taking a borrow from here. So there is a borrow for this case also. So in this way, we first find out that for each group there is a borrow are present. So as per the definition, we will be subtracting 0110 from the each and every uh, group. So after subtracting, we will getting 1. 1 minus 1 is equal to 0. 1 minus 1 equals to 0. 1 minus of this 0 is 1. And similarly here, similarly this. Now, uh, now the decimal equivalent of this is 5. This is 8. This is 9. So the answer is 58.9.
XS3 code. The XS3 code, also called as XS3, is a non-weighted BCD code. This derived name from the fact that each binary code is correspondingly 82414 word plus 011. It is a sequential code. It is a self-complementing code. Okay. In this case, the SS3 code is nothing but we are simply adding 011 3 SS3 to the 8421 code. Uh, Let us do an SS3 addition. In SS3 addition, add the SS3 number by adding a 4-bit group in each column starting from the LSD. If there is no carry out from the addition of any of the 4-bit group, subtract 011 from the sum term of those groups. If there is a carry out, add 011 to the sum term of those groups. Okay. Now let us understand with the example. Add 37 and 28 using SS3 code. So 37 is given by 011 01010 in SS3 code. 28 is given as 0101 and 1011. Now, I simply do the addition. You can see 0 plus 1 is 1, 1 plus 1 is 0, 1, 1 carry, 1 plus 1 is 0, and carry 1. As soon as I get carry over here, I take it to the next part, the decimal part. Now I am putting carry over here. 1 plus 1 is, sorry, this is 011, 101, 1101. Now this one is carried over here. So the 1 is 0, 1, 1 plus 1 is 0, 1, and 1. Now, as per the instruction, where the carry is generated, you have to subtract 0, 0, 1, 1, and if there is no carry generated, you have to add 0, 1, 1. Sorry, I'm again sorry. If there is a carry out, then you have to add 0, 0, 1, 1. If there is no carry out, you have to subtract 0, 1, 1. So in the lower part, the carry was generated. I simply add 0, 0, 1, 1 here. And in the upper case, there was no carry generated. Therefore, 0, 0, 1, 1 is minus over here. So after doing this addition, this is 1, 1. Again, carry 1, 1, 0, 1, carry 0, 1. And so you are finally getting 1, 0, 0, 0. And if you are subtracting over here, so 1, 0 minus 1 is 1, 1, 0 minus 1 is 1, you're finally left with 1. So this is the, now it's this is a related sum in the SS3 code, and now you can convert it into binary, you will getting 65. Now, SS3 subtraction. To subtract an SS3 number by subtracting each 4-bit group of a subtrahend from the corresponding 4-bit group of the binaries starting from the LSB. If there is no borrow from the next 4-bit group, add 0, 1, 1 to the difference term of such group. If there is a borrow, subtract 0, 0, 1, 1 from the difference term. Okay. Let us understand it by example. I'm subtracting 175 from 267 using SS3 code. Now 267 can be written as 0101, 1001, 7 is 1010, 175 is 0100, 7 is 1010, 5 is 1000. Now from 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0. Now, in this case, there is no borrow generated. Therefore, we will be adding 0, 0, 1, 1 to this part. Now, let us see the next part. In this, one is borrowed, 1 minus 0 is 1. For this is 1 0 minus 1, 1 is borrowed. Again, if the 1 is borrowed, you will be getting 1 over here. Finally, you are reminded with 0. You have to borrow from the another part, 1 0 1. So we are getting 4 times 1. Now, in this case, the borrow is taken from the next part. So we will be subtracting minus 0 0 1 1 from this. Just we are left with 0 1 0 0 because one has been already borrowed, and each downward you are getting 0 1 0 0. So yeah, after subtracting, both are the same numbers, therefore you will be getting 0. Here you have not taken any borrow, therefore you will be adding 0 0 1 1 over here. Now after doing this, you are getting 1 over here, 1 plus 1 is equal to 0 1 and so on. And after subtracting this, you are getting 1 1 0 over here. This is 0 0 1 1 here. And now it can convert into decimal part. And the decimal part is nothing but 92. So this is how SS3 subtraction is done. Now the next important code, which is very important code, ASCII code. This is known as American Standard Code for Information Interchange, pronounced as ASCII. Is widely used in alphanumeric code. This is alphanumeric code. This is basically a 7-bit code. The number of different bit pattern that can be created with 7-bit is 2 to the power 7, that is 128 codes can be generated. The ASCII can be used to encode both uppercase and lowercase character of the alphabet. Nearly about 52 symbols are used, and some special symbols are also being defined in the ASCII code in addition to the 10 decimal digit. It is used extensively for the printers and terminals that interface with the small computer system. The table below shows the ASCII group. Here, it's a table, it's a long table, which is defining the 52 characters, both in uppercase and lowercase, 10 digits. Even though the keyboard functions of space, del, null, and so on, at the rate is been defined. So using the LSB and MSB combination, you can see the using this table can define an ASCII code. This is again further continuing the ASCII code. You can see some special signs there: percentage, dollar, brackets, greater than, equal to, less than, question mark, and hyphen. Other many symbols are also defined in this ASCII code. This is basically alphanumeric code normally used in the computer interface, so especially in the case of keyboard. So now let us see the another important code, that is gray code. The gray code is non-weighted code. It is not a BCD code. It is a cyclic code because successive word in this differ in 1-bit position only. That's a you can say it is a unit distance code. Gray code is used in instrumentation and data acquisition system with the linear or angular displacement is measured. They are also used in shaft encoder, IO device, AD converters, and other peripheral equipments. Now let us see how can we define a binary code to the gray code. If an n bit binary number is represented by bn, bn minus 1, and so up to b1, and its gray code equivalent is given by gn, gn minus 1 up to g1, where bn and gn are the MSB, then the gray code bit are obtained from the binary code as follows. Now the gn, the first MSB is same as the binary code, that is gn equals to bn, and gn minus 1 is nothing but bn XOR bn minus 1, and so on. We just do perform the XORing, and we can finally get g1 is equal to b2 XOR b1. Now let us understand this by an example. Now we have to convert this binary number 1001 to the gray code. Now, as we said that the MSB is same, so we just take MSB 1 as 1. Now 1 XOR 0 is the next gray code. So 1 XOR 0 is nothing but 1. And 0 XOR 0 is 0. 0 XOR 1 is 1. So now this is your gray code equivalent of the 1001. That is 1101. Now, gray to binary code conversion. If an n-bit gray number is represented by gn and so on, gn minus 1 up to g1, and its binary equivalent is bn minus 1 up to b1, then the binary bit are obtained from the gray bits as follows. Again, in this case also, bn is equal to gn, the must be same. Bn minus 1 is bn XORing gn minus 1. Okay, and so on up till b1 is equal to b2 XORing g1. Let us understand this by an example. Now we are converting 1101 to the binary one. Now 1101 binary. So the MSB is same 1. Now we are XORing this gray GN with the BN minus 1. That is 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. The binary equivalent for 1101 is 1001. Now let us see some examples. What we have studied about. Now, here is an example to decode the following into BCD numbers. So, they are just simply take the four, grouping of four numbers. This four number is equal to 1, and this 0, 1, 1, 0, 0 is 4. It is 5. Let us move to the second part. It is this 4 combination is 2. Next 4 combination is 1. Then 4 combinations is 0, and finally this 4 combination is 7. So this is written as 0, 1, 2. Now let us see the next part. This 4 combination is 6. This 4 combination is 8. This 4 combination is 1. Then this 4 combination is 9. It is written as 9186. Now let us see the next part. This is again this 4 bits are equal to 1. This 4 bit equals to 6. Therefore, it is 61. This 4 bit is 0. Then this 4 bit is 5. This 4 bit is 1. Then last 4 bit is 5. 5 and 5, 0. This 4 bits are 1. Then 4 bits are 0. Then 4 bits are 0. And last 4 bits are 5. That is 5001. Okay. Now, let us find the gray equivalent of the following binary numbers. Let us see the first example. I have taken a MSB as 1, same. 1 XOR 0 is 1. 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 1 is 0. 1 XOR 1 is 0. Now, this is the code equivalent of the above binary number. 1 1 0 0 1 1 1 0 0. Now let us see the second part. Again here I'm taking the MSB part. Now 1 XOR 1 is 0. 1 XOR 1 is 0. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 1 is 0. 1 XOR 0 is 1. So this will be the gray equivalent of the above binary number. Similarly, the last one, I am copying the MSB now. Now 1 XOR 0 is 1. 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 1 is 0. Now, this one is here, the equivalent of the above binary number. Now, let us see the opposite part. Find the binary equivalent for like gray code. Now, taking the first example, now I'm copying this MSB. Now, this gray code is this binary code is this BN is XOR with GN minus 1. So 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 0, 1, 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. So this is your binary equivalent of the above gray code. Similarly, for the next example, I'm copying this MSB down. Now I'm doing this with XORing with the next gray code. 1 XOR 1 is 0, 0 XOR 0 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1. Now, the next example, here again I'm taking the one MSB down. Now I'm XORing this with the next gray part. 1 XOR 0 is 0, 1. 1 XOR 0 is 1. 1 XOR is 1 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. So in this way, we have got a binary equivalent for the above this gray code. Now, add 8765 and 7043 in a BCD code. Now, BCD number for 8765 is, for 8 it is 1000, for 7 it is 0111, 6 it is 0110, and 5 is 0101. For 3943 it is 0011, 9 it is 1001, and 4 it is 010, and 3 is 0011. Now simply I am adding the numbers. 1 plus 1 is 0, 1, 1 carry this, 1 plus 1 is 0, 1 again carry, 1 plus 1 is 0, 1 carry, and so on. And 0, 0 is this, 1, 0 is 1, 1, 1 is 0, 1, again 1, 0, 1, 0. Now 1, 1 is 0, 1, 1, 1 is 0, 1, 1, 1 is 0, 1. This is 0, and now the carry is generated over here. Similarly, this addition, you will be seeing that 1, 1 is 0, 1, 1, 1 is 0, 1, 1 is equal to 1, 1 is equal to 1. And for this, there is no carry. The correction is applied to this according to the BCD rule, and you are finally getting the correct answer. So with this, we have completed the digital codes, and we have seen different examples on that. From the next lecture, we will be starting the Boolean algebra. Okay, till then, bye.